Hello everyone, welcome to the Spatial Variability Lecture Part 3. My name is Sina Javankhoshdel. I am a Geomechanics specialist at Rocscience. My colleague Brigid, Cami and I are going to present in this lecture. This lecture is our last lecture, which is about spatial analysis in slide 2, 2018. In this lecture, I will first have a quick overview of the Spatial Variability lectures Part 1 and Part 2. Then I will talk about spatial variability in practice, and we will present a few case studies at the end. Previously on a Spatial Variability lecture series. Previously, we talked about three different methods of deterministic analysis, single random variable approach, and random limit equilibrium method. In deterministic analysis, we assign only one value of soil property to the entire slope, and then we calculate factor of safety. In single random variable approach, we have several simulations, and in each simulation, we sample from the distribution curve of the soil property and assign it to the entire slope, and then we calculate factor of safety for each simulation and a probability of failure at the end of the simulations. In random limit equilibrium analysis, soil properties vary spatially within the soil profile in each simulation, and they are not constant. Factor of safety is calculated for each simulation similar to SRV approach, and the probability of failure at the end of the simulations. Here is the procedure to carry out random limit equilibrium method in slide 2, 2018. First, we assign probability distribution to soil properties, and as you can see here, we have cohesion and friction angle with log normal distribution, mean and standard deviation defined. Then we define a parameter which is a correlation length in horizontal and vertical direction to carry out a spatial variability analysis. As we showed you in the previous lecture, if we have a small value of the spatial correlation length, the soil property is very fluctuated in the soil profile. And if we have a large spatial correlation length, soil properties vary smoothly within the soil profile. This is the only parameter that we need for the probabilistic analysis considering a spatial variability, which is very simple. As we mentioned before, the most complete probabilistic analysis is the one that has both a spatial correlation length and cross correlation. A negative cross correlation is reported between cohesion and friction angle, and a positive cross correlation between cohesion and unit weight and friction angle and unit weight. These cross correlations can be defined in material statistic dialog and in correlation section. After defining these parameters, now we generate n fields in several simulations. You can see here that the sampling method is Latin hypercube with 1000 number of simulations, and as we mentioned before, in each simulation we have a field, so we have 1000 fields. For each field, we carry out limit equilibrium method and we calculate factor of safety. As again we mentioned before, the factor of safety is calculated using non-circular limit equilibrium method with optimization. When we talk about limit equilibrium method, people think about circular limit equilibrium method, but the most accurate factor of safety is the one that comes from non-circular limit equilibrium method with optimization. And at the end, we calculate probability of failure as the number of simulations with factor of safety of less than 1 divided by the total number of simulations. And again, this method is called random limit equilibrium method, or RLEM. After the brief overview, in this section, I will talk about the spatial variability in practice. There are hundreds of studies about considering spatial variability in probabilistic analysis in literature. There are almost three main methods used in this area: one-dimensional spatial variability, random finite element method, and random limit equilibrium method. There are a few studies using one-dimensional spatial variability for real examples, such as James Bay Dyke or Sugar Creek embankment, as you can see in this table. Random finite element method, however, is used mostly for slopes with simple geometries, one layer simple slope, because of the limitations of the current available software packages using this method. Random limit equilibrium method, we started this method with simple slopes, similar to random finite element method. But the current version of Slide 2 2018 can handle any type of geometry that we are going to show you today, how you can handle these types of geometries. Let's talk about these methods in more detail. One-dimensional spatial variability is the simplest way of considering a spatial variability in probabilistic analysis. In this method, a slip surface is divided into different segments equal to the spatial correlation length, delta L, as you can see in this figure. Then a sample from a distribution curve of the soil properties is assigned to each segment. In this method, there is only one spatial correlation length value along the slip surface, and horizontal and vertical spatial correlation lengths are converted to only one value. So it is not accurate, especially when one of them is very large. This is one of the examples in literature that one-dimensional spatial variability is used in probabilistic analysis of a real model. As you can see here, the purple sections are the segments equal to the spatial correlation length, which is equal to 30 meter in this example. We will model the same example using a Slide 2 2018 as well with random limit equilibrium approach, and we will compare the results at the end. Random finite element method is a combination of random spatial fields together with finite element method to find failure mechanism. In this method, a spatial field is created on a finite element mesh using local average subdivision method, as you can see in this figure. The shear strength reduction method is used to calculate factor of safety in this approach. In the current random finite element software packages, gravity turn-on method is used to calculate probability of failure instead of doing SSR in each simulation. Gravity turn-on only shows failure or not failure in each simulation without giving any factor of safety. The random finite element method is limited to academic purposes, and that's why it is slow and cannot handle complex geometries. They also have convergence problems for small mesh sizes. As we explained before, for random limit equilibrium method analysis, we create a spatial field on a mesh using local average subdivision method. Factor of safety is then calculated using non-circular limit equilibrium method with optimization. The output parameters in this method will be deterministic factor of safety, mean factor of safety, and probability of failure. Any type of geometry, any mesh size, and any spatial correlation length can be handled using this method. These models that you can see in these examples are the models with they are cohesive slopes with linearly increasing cohesion. As you can see, the top of the model is blue, which means that it's a weak material, and as it goes down, it becomes stronger. So it is a linearly increasing cohesion case. Since random limit equilibrium method and random finite element method are the most accurate methods for spatial variability analysis, we compared these two methods for a few cases presented in literature. This is a simple slope with 2 layers of soil from Huang et al. 2010. This is the type of geometry that software packages using random finite element method approach can handle, just simple slopes. Deterministic factor of safety is the same for both examples, as you can see in this table. It is 1.2. However, probability of failure using random limit equilibrium method is 14.5%, and using random finite element method is 10.5%. As you can see, in this case, random limit equilibrium method has found more failure surfaces compared to random finite element method, and it gives higher probability of failure. This is another example of simple slopes using both methods. As you can see, both RLEM and RFEM, the left figure, give the same probability of failure for the same value of the spatial correlation length. However, the right plot shows that the computation time using random limit equilibrium method was 25% to 46% of the time required to complete the matching RFEM simulation. This is only for 5,000 simulations in this example, and that's why random limit equilibrium method is the only option for complex geometries. Where random finite element method takes days, random limit equilibrium method takes hours or sometimes minutes. Here is a general comparison between three approaches. One-dimensional spatial variability is fast. It can handle complex geometries, but it is not accurate. Random finite element method is accurate, but it is slow in the current software packages, and it can only handle simple geometries. And it has also convergence problem in small mesh sizes. It is mostly used for academic purposes. That's why there is a lack of commercial software packages in the market that can carry out random finite element method. Random limit equilibrium method in slide 2018 is as accurate as random finite element method, but it is much faster. It can handle complex geometries, and it does not have any convergence problem because it is non-circular limit equilibrium based. All the comparisons and comments that we have had about these three approaches came from these journal and conference papers that you can find them on Google Scholar or ResearchGate by searching our names. In this section, we are going to talk about real geotechnical examples, not just simple geometries, using random limit equilibrium approach in slide 2018. This is one of the real case studies. This is Mount Polley Tailings Dam in British Columbia. The story behind this example is it failed in 2014, and there were a lot of investigations to find the reason. They found that there was a weak layer at the bottom of the tailing dam that was not considered in the design of the dam. As you can see here, this thin layer at the bottom. The purpose of presenting this example is to compare the results of three different cases of non-circular with no optimization, with Monte Carlo optimization, and with surface altering optimization, that we have these options in slide 2018. This is a challenge for the search method to find the weakest failure path that goes through the weak layer. The other point here is the green and orange regions are strong materials, and the search method has to find a path that goes behind these regions as well, which is another challenge for the optimization technique. Let's look at the deterministic analysis using these three optimization cases first. As you can see in this table, for the case with no optimization, factor of safety is 1.35, and if you look at the failure surface, you can see that it is almost circular. For Monte Carlo optimization case and surface altering optimization case, as you can see, factor of safety is 1.26, and you can look at the failure surface that it is not similar to the case with no optimization. And you can see that the failure surface goes through the weak region at the bottom of the slope. We compared the deterministic factor of safety in a slide using surface altering optimization with the strength reduction factor in RS2 software using shear strength reduction method. RS2 software is our strong finite element software package that has a lot of abilities. One of them is a slope stability analysis using shear strength reduction method, as you can see here. If we compare the failure surfaces in both methods, you can see that they are very similar, and also the factors of safety, they are both 1.26. This shows the strength of the surface altering approach to find first the failure mechanism and also the factor of safety, similar to the finite element method. To carry out a spatial variability analysis, we need to have a spatial correlation length. For this example, we had data for CPT tests at different locations, enough for measuring a spatial correlation length in vertical direction, but they were not enough to measure a spatial correlation length in horizontal direction. We measured the vertical spatial correlation length of 1 meter, but for horizontal spatial correlation lengths, we assume that it is 400 meters. So we have 1 meter vertical spatial correlation length and 400 meters horizontal spatial correlation length. This is called anisotropic spatial correlation length, and I'm going to show you what that means. Let's see what happens when we have isotropic and anisotropic spatial correlation lengths. The top figures are isotropic cases that we showed before with a small and large spatial correlation length. The left bottom figure is for the case that vertical spatial correlation length is much smaller than the horizontal spatial correlation length. For example, for reinforced retaining wall cases that we compact soil in small vertical layers. And as you can see here, we have horizontal regions with similar values of soil property. The opposite is the right bottom figure, that horizontal spatial correlation length is 1 meter, which is small, compared to the vertical spatial correlation length, which is 1000 meter. And as you can see, in this case, we have vertical layers of material with the same soil. I'm going to pass the presentation to my colleague Brigid, and she's going to continue the example with the live demo in slide 2018.
Thank you, Sina. So now let's look at this Mount Polley example in slide 2. So this is our model. As we've talked about, this bottom layer is the very weak layer. So let's first go to our project settings. And we see that we're using the GLE Morgenstern-Price method, which is suitable for non-circular search, and we're using 50 slices. So we see that we're using the GLE Morgenstern-Price limit equilibrium method, which is suitable for non-circular search, and we're using 50 slices in this case. And if we click on statistics, we see we're doing Latin hypercube sampling and 10,000 samples. Just keep in mind that these settings in the methods are going to be what we use for all 3 of these examples. It's pretty standard. So now let's take a look at our random variables. We're going to go to Statistics, Materials, and we see that we have random variables defined for the tailings, the upper till, and for our weak layer. And we can also see that the horizontal correlation length is 400, whereas the vertical is 1. So the 1 we measured from data, and the horizontal, we're not considering it in this example. We're only studying vertical. Okay, so the first thing we want to do after we define spatial variability, of course, is check our field. And we can do that from the Property Viewer button. And because this rock material is so strong, the legend adjusts to account for that material. So I'm going to use this filter, which says show variable only, and turns off the constant materials. And we see now only the cohesion random variable for the weak layer. If we switch to friction angle, we see a nicer field because there's more friction angle random variables. And we can also see that this bottom layer is bluer compared to the others, which means it has a lower friction angle, or it's weaker. It's the weak layer. Okay, and another thing to look at is our mesh. So if we turn on the Show Spatial Grid button here, we can see how small the mesh is in this model. And that's of course because our vertical correlation length is 1 meter, so the mesh is adjusting to that size. So such a small mesh makes this quite a complex model. Okay, so we've checked our field. Now we can close the property view. The goal of this example is to see what kind of effect the optimization method has on the results. So to do that, we're going to create 3 child scenarios here. So I'm going to click Add Child Scenario 3 times. And I'm going to rename them No Optimization, Monte Carlo Optimization, and Surface Altering Optimization. So we're going to go to the first scenario, and we're going to go to the Surface Options button. And we see we're using non-circular, auto-refine, and we're going to turn off optimization for this first scenario and click OK. In the second scenario, we're going to do the same thing, and where it says optimize, we're going to click on settings and change it to Monte Carlo optimization. The rest of the settings we suggest leaving as default. And we'll click OK. And for the final scenario, we're gonna set that to surface altering. And because that's the default setting, you can see it's already set here. Okay, so now we're ready to look at the results. If we go to interpret, here we have the results in 3 panes. So this first one is no optimization, the second is Monte Carlo, and the third is surface altering. The red surfaces you see right now are the deterministic surfaces. So you can see without optimization, it's almost circular with a high factor of safety of about 1.3, whereas with optimization, the surfaces are very similar for the deterministic case, and the factor of safety is about 1.26. If we look at probability of failure, we see that no optimization has a PF of 0%. Monte Carlo 0.09% and surface altering 0.183%, which means surface altering found the most failed surfaces for the same spatial fields. So let's take a look at those fields. So I've locked zoom here so I can look at all the models at once, and I'm going to turn on property viewer for all. And again, I'm going to look at friction angle. So first, let's lock our property viewers, all 3 scenarios, and switch to friction angle for all 3. And I'm also going to filter out the constants like we did in the modeler, so that we're only looking at the spatially variable materials. Okay, so what we're looking at now is simulation 1 out of our 10,000 simulations. So the field is identical between all 3 of these scenarios, and we see that for the exact same field, the no optimization case had a factor of safety of 1.3, the Monte Carlo 1.16, and the surface altering 1.14. So for the same field, the surface altering found the lowest factor of safety surface. Okay, so this gives us an idea of why optimization is important and what kind of effect it has on our results. Now let's return to our presentation. So here we've summarized our results, which we just discussed, and so again we conclude surface altering finds the most failure surfaces. But the other big advantage of surface altering is that it does so in much less time. It takes about 1/5 of the time for surface altering to optimize surfaces when compared to Monte Carlo. So certainly it's the recommended optimization method. The second example we're going to look at is a design for the dikes of the James Bay Hydroelectric Project in Quebec. There's a lot of data collected on the uncertainty and spatial variability of the soil in preparation for this design, which makes it a commonly studied case. Recall that this is the example we mentioned earlier that L. Romney studied using one-dimensional variability. Let's first take a look at the deterministic slip surface. The global minimum surface found by L. Romney was circular, with a factor of safety of 1.4. Meanwhile, using non-circular search with surface altering optimization, we found quite a different surface, and we found a factor of safety of 1.1. Alright, so let's take a look at that. So the project settings here are going to be similar to the previous. Let's take a look at our material properties. So if we go to the Define Materials button, we see we have an embankment on top, 3 layers of clay, and a till. Now, RLEM assumes that this bottom material, the till, is much stronger compared to the other ones, so that the slip surfaces do not cross it. And to ensure that no slip surfaces go through this material, we set the strength type to infinite strength. Now let's take a look at our statistics. So these random variables are defined based on what was actually found in the field for these properties. So we can see various random variables are defined for some of the soils. And we also see we have a correlation length of 30 meters in both directions. Notice that the correlation length is isotropic, as measured by RLEM, and this is because one-dimensional spatial variability can only take isotropic correlation. Okay. So once again, we've defined our random variables. We want to check the field. So we go to our property viewer. Once again, we can filter out the constants and just look at variables. This is cohesion, friction angle, and unit rate. Looks good. Okay, so in this example, like we said, we have 30 meters isotropic correlation length. Here, our goal is to look at what kind of effect correlation length has on the results. So to do that, we can do a correlation length sensitivity analysis by going to Statistics, Spatial Sensitivity, and I'm going to set the material to all materials, which means it will change for all of them at once, and I will set the property to isotropic, which means it will change for both x and y directions. And we'll start from a correlation length of 10, go to 70 in 4 steps. And what that does is it creates 4 child scenarios in this group, each one with a different correlation length. So the first one is 10 meters. If we go to Statistics Materials, we see it's 10 for all of them. And if we go to the 51, we see that's 50 themselves. Okay, so let's take a look at the results, see what kind of effect correlation length has on the results. Alright, so I'm going to close this master scenario, and we're just going to look at our 4 child scenarios. Let's tile them to view them better. Now, the first thing you might notice here is that the same red surface is shown in all 4. Remember that this red surface is the deterministic global minimum. So since we're only changing correlation length, that's a probabilistic parameter. The deterministic global minimum stays the same for all. Okay, so this top left scenario is the 10 meter correlation length, then 30 is down here, then 50 and 70. So we can see that probability of failure is increasing, but we'll look at that later. First, let's take a look at our property viewer. So I'm going to lock all of these scenarios so that I can look at the property viewer for all of them. Then I'm going to link all the property viewers so that these settings apply to all of them. And I'm going to show variable only. And let's just look at cohesion for now. So like we said, the top left is the 10 meter case. And that means that the areas that are similar are about 10 by 10 meters. And we see that this orange region, for example, is small. As correlation length increases to 30, the orange region gets bigger, to 50 bigger, and to 70 bigger. So that's a good way of visualizing the correlation. So now another cool feature in slide 2, 2018 is the ability to graph values between scenarios. So we can plot these probability of failures. Let's do that by going to Data, Graph Scenarios, and we're going to select all our scenarios. We're going to set the plot type to spatial correlation length. Since x and y are the same, we can pick either one. Go with x. And since they are the same for all materials, we can pick any material. The default is to graph factor of safety. I'm going to check this box to graph probability of failure instead. And we plot. And as expected, we can see that as correlation length increases, the probability of failure also increases. So as correlation length increases, we're reaching that single random variable approach case, or the case where correlation length is infinity, and so probability of failure goes up. Okay, so that's our James Bay example, and we see the effect of correlation length on our model. The next example we're going to look at is the Sugar Creek embankment in Iowa. So on the left here, you can see the geometry of the model. The weak layer here is the orange one, the highly weathered shale. Cho studied this model in 2007, and you can see this image from the paper on the right. He used non-circular search with Monte Carlo optimization with one-dimensional spatial variability. So first, let's just look at deterministic results. This black line is his deterministic slip surface, and the factor of safety we got was 1.59. So we built the same model in slide 2 and in RS2. We used non-circular search with surface-altering optimization, and we obtained the same surface with the same factor of safety. Running it with shear strength reduction in RS2, we got the same factor of safety, 1.6, and you can see the surface also looks the same. Okay, so now let's take a look at this model in slide 2. So this is the geometry of our Sugar Creek model, and we can go to material properties and look at our various materials. So we can see that this highly weathered shale is weaker relatively compared to the others around it. And then we can click on statistics. And again, the random variables defined here are the ones found in the field. And in this case, we're using a correlation length of 40 meters. So we've defined 4 child scenarios in this example. SRV without correlation, SRV with correlation, spatial without correlation, and spatial with correlation. So in this example, we want to see what kind of effect using spatial has and what kind of effect using cross-correlation has. The scenario names are pretty self-explanatory. If we click on SRV without correlation and go to statistics materials, we see that no correlation is defined. If we click on SRV with correlation and go to statistics materials, we see that correlation is defined. So between cohesion and friction angle, it's -0.5 for all the materials. Similarly, the spatial ones are both spatial and without correlation, and the other one is spatial with correlation. Okay, so as always, we want to check our fields first. So let's take a look at this one. Now this is a very interesting case because this bottom material is incredibly strong. So let's just quickly look at that in material properties. This bottom material has a cohesion of 675 kilopascals. So when we look at our fields here, we're only able to see the bottom field because the legend auto-adjusts to the range of cohesion values. So to account for that, we can use this option called normalized spatial contours to standard deviation. And if we check that, our legend goes from cohesion in kilopascals to cohesion in standard deviations. So that means that this blue region is the mean -2 standard deviations, the red region might be the mean +6 standard deviations, and so we see each field relative to the properties of that material. So that's helpful when we have materials that have very different properties. Let's take a look at friction angle instead. Another interesting thing to note here is that the boundaries of each material are quite different. There are some very thin and long ones. So if we turn on spatial grid, we can see that the mesh auto-adjusts to the material boundaries. So you can see for our highly weathered shale, the mesh is much smaller compared to the others. Now, out of curiosity, let's see what happens if we look at the property viewer for one of the non-spatial cases, such as the SRV without correlation. Well, the property viewer auto-adjusts to the first property that it finds, and in this case, it's pore pressure because we have a water table defined. So this is another way of looking at pore pressure. Okay, so in this example, we want to see what kind of effect does correlation have, what kind of effect does spatial has, so let's look at the results. Okay, so now we're in Interpret for Sugar Creek. Let's take a look at our probability of failures. So we can tile the views, and I'm going to lock zoom in out, and we see on the left we have SRV without correlation and SRV with correlation, probability of failure goes from 3.3% to 0.2%. Considering correlation brought PF down. And on the right we have spatial without correlation and spatial with correlation, and it goes from 0.6% to 0.01%. So again, considering spatial brings probability of failure down. So we've summarized these results in the PowerPoint. And so as we go right in this table, we consider correlation, and as we go down, we consider spatial. So we see probability of failure goes down, and we get a more realistic value. Since this is a stability problem, all three of these other probability of failures would not be acceptable for design, but 0.01%, when we consider spatial and cross-correlation, would be. And keep in mind, this is relative to our deterministic factor of safety of 1.6. We can also look at histograms of our 4 scenarios. So once again, as we go to the right, we consider correlation. As we go down, we consider spatial. And in both cases, our distributions get more narrow, more accurate, because we've removed some uncertainty from our model. And the narrowest, most precise distribution is the one that considers both spatial and cross-correlation on the bottom right. Okay, now let's go back to our model. And let's take a look at one of our scenarios. So let's look at spatial without correlation, for example, and the probability for that. And I'm going to look at cohesion since it's a little nicer. So we can see the first slip surface and its factor of safety, second, third, and so on. This one is a nice one because you can see how the slip surface follows the blue region in this weak shale material. Now, say we want to confirm the factor of safety for this specific simulation, simulation 3, using shear strength reduction. Well, we can export our field as a discrete function and import it into RS2. So what that means is, if I show the grid here, we can export the value assigned to each cell and import it as a discrete function. And to do that, we go to File, Export, Export Sample as Discrete Function. And first we do it for the first material, the compacted fill, and click OK. And save. And then we do it for the second material, alluvium, and click OK. And save. And so on for the other materials. So now I'm going to open RS2. RS2 is our two-dimensional finite element software. It's sort of an all-purpose finite element software for Geotech. But you can also use it for slope stability to do shear strength reduction. So the first thing we do here is we're going to import our slide file. So we go to File, Import, Import Slide, and we import our file. That's pretty easy. Note this is the deterministic file. So if we go to Materials and Staging, and we look at our materials, there's no spatial variability assigned to this. This is the deterministic values we entered in the material properties in slide 2. So we see the failure criterion, a lot of options available in RS2. And we're going to change this from more Coulomb to discrete function. Then we're going to go to Edit, and we're going to rename this first one Fill, and we're going to import our discrete data. So we go to Import, and we select the compacted fill, and we see that we have X and Y location data and cohesion and friction angle for this fill. Then we're going to add the second material, so we do Add, and we rename that alluvium, and we import the alluvium discrete function. So the same thing, location and material properties. And we click OK. So then I'm going to set the first one to fill. Then I'm going to go to the alluvium material, discrete function, alluvium, and OK. So we see that for the first two materials, each triangle represents a value assigned at that location. Now I have already imported them all and computed the results, so let's go to that file here. And let's take a look at the results. So if we go to Interpret, okay, the first thing we see is the surface. So remember, this is for that third simulation in slide 2. So we see that the surface going through the shale is the same. We see that the critical shear strength factor, 1.16, as shown on the top here, is the same as the one found for the simulation, 1.165. And we can even compare the fields. So if we look at the field here, in RS2 we can go to this data viewing dropdown and go to user data types and select friction angle. And we see that the field is the same. So now let's go back to our document. So once again, it's easier to view them side by side. So we see the slip surface is the same and the field is the same. So this is sort of a way to confirm that non-circular with optimization gives the same result as shear strength reduction, even with a spatial field. Okay, so in this 3-part spatial lecture series, we've focused on 3 things. In the first lecture, we talked about probabilistic analysis, or the single random variable approach. And we said that to go from a deterministic analysis to SRV, you only need a couple of additional parameters. You need distribution types for your random variables and their associated parameters, such as mean and standard deviation. In the second video, we talked about spatial analysis, or the random limit equilibrium method, and we talked about that the only additional parameter you need to go from SRV to RLEM is correlation length in the x and y directions. And another thing we've tried to stress is the importance of considering cross-correlation in your models. So a full analysis should consider both spatial analysis and cross-correlation. So, in conclusion, why do we need spatial? Doing a deterministic analysis makes some very strong assumptions. 1, it assumes that we are certain about our parameter inputs. 2, it assumes that we are certain that our model is homogeneous. And so, it assumes that we are certain about our single factor safety value. A spatial analysis allows us to account for these uncertainties to get the most accurate probability of failure available. We've also learned that only a few additional parameters are required to go from deterministic to spatial, so it's not very cumbersome. And in this way, an academic venture for the last 30 years or so, with slide 2, can be put into practice. So now we can run spatial analysis because we have parallel processing, fast optimization methods, and easy input and visualization. Thank you for watching our video lecture. If you have any questions or comments, please send us an email at statistics@rocscience.com. Thank you.